So now let's switch gears and kind of start some chapter 2 stuff. Chapter 2 is all about alkanes. This is our first class of organic chemical that we're going to learn about here. It's the simplest of the organic chemistry classes because it's compounds that contain, so these contain only carbon and hydrogen. And these molecules contain only single bonds. Okay, so this is what defines an alkane. So something like this would be an alkane, right? All carbons and hydrogens, all single bonds. Something like this could also be an alkane. They don't have to be a straight chain to be an alkane. You can have a branched alkane as well. Okay, and before we sort of go on, the first thing that we're going to do with like every functional group that we learn is learn how to name it. So there are going to be these rules that we have to apply to naming these compounds. Actually, previous instructors kind of had done a survey of people in careers that, you know, a lot of you guys were actually plant science, animal science type majors. Which was awesome because actually watching the videos, this is like the first group of students I've had where like a majority of people like to cook, or a significant number of students like to cook. Never ever seen that in my college class before, which is awesome because I love to cook. So I'll try my best to try to relate stuff to the world of cooking. Unfortunately, alkanes are more like gasoline than they are like any sort of ingredient in a dish, but nonetheless. And it turns out that naming these compounds, have a familiarity with the names of organic compounds, is one of the most useful things for you guys going forward. So nomenclature is going to be something that we do every time we introduce a functional group. We're going to learn how to name it. Before we do that, though, I want you guys to convert these structures into bond line structures, because we're going to get really good at looking at bond line structures, so we don't have to sit here and draw these Lewis structures every single time. So convert these two structures to bond line structures for me. All right, so this, our bond line structures for our alkanes are like the most simple bond line structures, because again, in a bond line structure, carbons and hydrogens are implied, and alkanes are only carbons and hydrogens. So in this case, I have 1, 2, 3, 4 carbons. I should have 1, 2, 3, 4 carbons represented in my bond line structure. Again, the whole shtick about the bond line structure is just look at how much quicker it took me to draw that than the actual Lewis structure. For this, I would have this central carbon that's bound to 3 other carbons. If you made it like a T, that isn't exactly wrong, but it does look weird. If there's, we would do that if there's 4 bonds to that carbon. If there's anything else, we tend to do this like zigzaggy kind of pattern here, right? And then we would branch off of that zigzag.
So do angles matter when we draw these bond lines and stuff then?
I mean, yes and no. I will be pretty forgiving about it, but I will say that it would look very, very weird. Like if you go on and show it to another chemist, they'd be like, why the hell did you draw it like that? Like the default is to be zigzaggy. And it's only ever if you have a carbon that's bound to 4 other carbons, something like this. this you would draw as like a cross because there would be no other way to do it. But other than that, you want to default to doing these kind of zigzaggy things. All right, and especially like with the this one here that I colored in green, there kind of wouldn't be a real way to do it without the zigzags. I don't know how you could do it with like straight lines, like I guess all right angles or something. I don't know. Bottom line, it looks weird. It's kind of like, you know, some things in chemistry are just convention. It's like if I asked you how many brothers you had and you told me you had 4 halves, it'd be like, all right, I mean, that is the same thing as 2, but that's just a weird answer. Okay, and so both of these we'll see, you can kind of convince yourself of, has this formula C4H10, but they have a different connectivity of atoms. So everybody in the chat, tell me, what did we call these 2 molecules? What would they be? They're a certain type of isomer. This is a vocab word you definitely want to know. So these would be, if you have the same formula, but a different connectivity of atoms, either a structural isomer or a constitutional isomer. Both of those are the saying the same thing. They're totally synonymous with one another. But yeah, I mean, you can totally be expected to draw me 2 structural isomers of whatever. These are things that have the same formula, but have a different connectivity of atoms, right? So this one we would call our straight chain. This one is branched. And for the, you know, basically the smaller the number of carbons, the fewer the structural isomers are, right? When you go up to something like C8H18, all of a sudden that one has a crap ton of different structural isomers because you can start branching at all these different points. Okay. So yeah, so these are alkanes, things that just have carbon and hydrogen. They just have single bonds. Again, where we see them in nature is these are our fuel sources. So like gasoline is just a mixture of a bunch of different alkanes. They are fairly unreactive. The one thing that they do very well is combust, and they release a crap ton of energy when they do combust. And we'll talk about a combustion reaction later on, but that's you know, again, that's what's gasoline's doing for your car, right? It's going through a combustion engine. It's releasing a ton of energy, which is what's actually powering the car to go forward. Other than that, these don't have that many reactions associated with them. They're pretty boring molecules. Basically, they're very happy. They're very stable on their own. So we're going to talk about properties of alkanes here in a bit. But again, the first thing that we're going to do is learn how to name these. And we're going to start with the simplest ones, the straight chains. So let's actually just do a new page. So all of our functional groups will have different suffixes associated with them, things that you tack on to the end of the name. And for alkanes, that suffix is ane, kind of built into the name. We also have this list. Also, let me make it pretty. We have this list of number of carbons and then these prefixes. And let me just say real quick, the whole purpose of nomenclature in organic chemistry is so that the name of a molecule uniquely points to its structure, right? When you say the name of a particular molecule, you know exactly what you're talking about. There's not any ambiguity of maybe I'm talking about this structural isomer of this one. These 2 different structural isomers that I drew will have different names associated with them, right? So the name is pointing directly to the structure. So the first bit of information we need is how many carbons there are. Okay. So for example, the simplest alkane would be just a single carbon, and this has the prefix meth. So this guy right here is methane. If it has two carbons, this is the prefix eth. So this would be ethane. 3 carbons is prop. So I'm going to draw it as the bond line structure here. This would be propane, right? So you might have a propane grill. What's in that little tank that you get refilled is this 3-carbon alkane here. And let me just take a second to, again, just stop and show how these names are being constructed. We have the number of carbons, which is going to uniquely point to one of these prefixes. So we lay down the prefix, and then we tack on that common suffix for alkanes, ane. So same thing here. I had 2 carbons. That points to the prefix eth. And then I tack on that common suffix ane. 3 carbons, prop, tack on that suffix ane. Okay. 4 carbons is bute, as in butane. That's also a common source of fuel. Like if, you know, for those cooks out there, your blowtorch or whatever that you use for like creme brulee, that would be a butane torch. So that has a 4-carbon alkane in there. And then actually the first 4, I think, are the hardest. Though from there, it gets a little bit easier because it corresponds to what we remember from our geometry classes. So 5 is pent, 6 is hex, 7 is hept, 8 is oct. Those are kind of the most common, but just to be complete, 9 is non, and 10 is dec. Okay, so I'm going to put down a few examples of alkanes here, and we can use our little prefix cheat sheet for now. Of course, this is something that you're going to have to know for the exam. Again, what the ones that I would kind of just focus on are the meth, eth, prop, bute. I would try to chant that over and over and again and get that stuck in my head, because those are the ones that are the hardest. The hept, the hex, the pent, the oct, those are ones that sound way more familiar. But meth, eth, prop, bute, those are the first 4 that are a little bit funky and unique to chemistry. Okay, so I'm gonna put down some structures. I'm gonna do some structural formulas, some Lewis structures, as well as some bond line structures to get everybody really good at practicing our bond line structures. And you guys just tell me the name of these alkanes that I'm writing here. And again, for right now, we're gonna do just straight chain alkanes. We'll get into how to deal with the branches. Yeah, probably not even this class, but next class. Oops. Okay, so with my first one, let's put it in the chat. Yep, so far so good. And we will definitely complicate things a little bit, but when it's the straight chain, it's pretty straightforward, right? So just count the number of carbons. Actually, let me see the next one to this bond line structure. Make sure everybody's counting their carbons in bond line structures correctly. Cool. 1, 2, 3, 4, 5, 6, 7. So that would make this a heptane. Okay. Now this next one I put down just to be kind of a pain in the butt. And to stress something here about like how these things are written. There is this little kink here, right? All of a sudden I go from drawing it in this straight line and then it kinks up. Nonetheless, this is still a straight chain alkane. I just kind of wrote it a little weird, right? A branch point means a carbon that's connected to more than 2 other carbons. So this wouldn't be a branch point here. It's just kind of drawn with this little kink. If I was to do a sort of bond line structure that's kind of a similar logic, it'd be like if all of a sudden I started going up and then over with it, something like this. It's still a straight chain alkane. I still have this one contiguous set of carbons here. I've just drawn it with like this kink in there. Okay, so I just want everybody to kind of convince themselves that this is indeed still a straight chain alkane, just kind of drawn a weird way. All right, and this may seem very weird now, but when we start getting into branch points, it's going to be very important because, and I'll just give you kind of the preview now for where this is going to go. But the first step in naming an organic compound that has a branch is to first find the longest continuous set of carbons. And that's what we call our parent chain. And then from there, we'll go on to talk about the things that stick off of our parent chain. But so being able to identify a longest contiguous set of carbons. So even if there was a methyl group here, colored in orange is still the longest continuous set. So the orange would be my parent chain, and this will be my substituent. Okay, so we'll pick up with naming branch compounds next time. Again, your OWL, the first set is due on Friday. Now that we've all had some experience with it, if you guys had any sticking points, please contact me and let me know. Again, it might seem like a pain in the butt, but once you get used to it, it'll be really nice to get immediate feedback as to whether you're drawing structures correctly. And so that's the whole point there. All right. So yes, give me your name in the chat before you go. And then I will see you on, what's today? Wednesday, Friday?
Thank you.
Yep, have a good one.
Can you hear me?
Now I can.
I actually have a question.
Yeah.
So on the OWL thing, it was telling me the due. I got it done last night, but it was telling me the due date was the 6th.
I just so there's two. So the assignments were split in half. 3 of them were originally due tomorrow, and then 3 of them were due on the 6th. And then I just extended the ones that were due tomorrow. I extended to Friday.
Okay, I ended up doing them all because Canvas told me they were all due last night, and then the OWL thing was saying, "Oh,
no, you're totally right. I changed the due dates on OWL and didn't update it on Canvas."
Oh, okay, I was kind of confused. Thank you, man.
No, but listen, if you did like rush and submit it and didn't get full credit, just let me know and I can reset it for you and you can retry it.
I didn't. I'm good, but thank you.
Okay, cool.
Have a great day.
Yeah, you too.
Professor,
yeah,
I have a quick question. Are you able to set office hours for maybe tomorrow or some other day aside from Friday?
I'm not gonna have like office hours, but if you want to arrange a meeting, we can.
Yeah, cause I texted you yesterday and I had a little bit of trouble doing some structural isomers on
Yeah.
I understand how to do it, but what I didn't understand is how to maybe use the tools, because I click on like carbon and it gives me carbon with like all the 3 hydrogens, and then when I click on nitrogen and I try to bond it together, it gives me like another nitrogen with another 2.
Yeah,
I
so
don't
it'll
know.
always fill in the hydrogens for you because it's not going to let you put down a carbon that doesn't have like the complete octet. So as soon as you put down a carbon, it's going to immediately fill in the octet.
Okay,
But
got it.
nonetheless, we can work through it. So do me a favor, send me an email and we can figure out a time. Tomorrow is Thursday, so I'm not going to be done until like the 5:30 range. So it's going to be in the evening sometime.
Yeah, that's fine. That works with me.
Okay, cool. All right, well, send me an
um,
email to remind me, and then we can set it up. We'll like nail down a time.
Yeah, that's fine. The only thing is that I do have class tomorrow until 6:15.
That's fine. So we'll meet after that.
Okay, that's fine. Thank you.